The title of the current presentation and paper is the optimization of a green hydrogen storage based on end user consumption profile. The paper is presented by Mohammed Sameti and Owen Siron from School of Chemical and Bioprocess Engineering and UCD Energy Institute, University College Dublin, Ireland. Let's first look at the terminologies. What does green hydrogen mean? Basically, if we generate hydrogen from any renewable or green sources, the hydrogen that is generated is called green hydrogen. For example, we know that we can generate hydrogen through chemical processes, and not all of them are from renewable energies. Those types of hydrogen that does not come from green sources is called gray hydrogen. So for green hydrogen, which comes from, for example, solar energy, it can be solar heat or solar electricity, biomass, bioenergy, wave and tidal energies, the wind energy and geothermal energy, plus hydropower. If the hydrogen is generated by these sources, it is called green hydrogen. Now, green to green technology is the coupling or integration of those resources with appropriate environmental friendly storage systems, such as compressed air, pumped hydro, hydrogen and fuel cell, and the mechanical ones where flywheel is one of them. Also, battery can be included here, not all of them, some of them. So if the, for example, energy from solar, from sun, for example, electricity, solar electricity, runs the electrolyzer to generate hydrogen, that hydrogen is the green hydrogen, and the technology that we use is called the green to green technology. The example that I just provided is one of the most applied technique to generate green hydrogen. So using electricity from PV as the input for the electrolyzer, and then generate hydrogen. And this is the concept that we use in this paper as part of our modeling. But the other issue that we have is, because the nature of the solar energy is an intermittent nature. That means that there is no sunshine during night or when there is cloud. So we need to store hydrogen for those hours or for those periods that irradiation is not provided. Hydrogen storage systems, or HSS systems, as you see from the graph here, covers three main storage form or categories, which is the electrochemical, mechanical, and pure hydrogen storage. If you look at the scale of the hydrogen and fuel cells, we see that it is on the right side of the graph. So it covers the high power rating based on the module size. And if we look at the discharge time, the hydrogen systems and fuel cells can be used as the hourly storage systems, so not for lower resolution storage systems. And hourly storage systems can be used for either commercial and industrial and residential sectors. So that's a suitable storage systems, especially if we look at the price or cost of the systems. We see that pumped hydro covers part of it, and it covers like the highest level for power. But if you look at that, we can see that pumped hydro needs a wide area for the storage systems, but hydrogen and fuel cells are much smaller, and we can use them for a variety of applications. The same concept applies to compressed air energy storage, which is a type of energy storage between the pumped hydro and the hydrogen in terms of the form of the storage, and also in terms of the power rating. So the technology that we use here is the compressed hydrogen, which we call it CGH2, and that G stands for gas, so compressed gas, but which gas it is? H2 or hydrogen. So actually we use a tank, and similar to the storage of hot water for the solar systems, we are going to use the tank to store the hydrogen in the compressed format. In our paper, the configuration that we proposed is to use the, first of all, a hydrogen load. So it can be a residential load, it can be a commercial load, or it can be industrial load, or it can be a community load. So 4 types of load can be considered here. For our paper, we considered a residential type of load as our first scenario or primary scenario. And as we just mentioned, we need to store hydrogen in the compressed form. The primary electricity provider is the PV panels, which generates electricity in the form of direct current or DC, and that DC current feeds the electrolyzer. As the backup, we need grid, and since grid is in the alternative current form, so we need to include the converter as well. Basically, the round-trip efficiency of the compressed hydrogen tanks are 50% and less than that. So that's one of the drawbacks of the those types of the hydrogen tanks. And if we increase that, that will really improve the overall efficiency of the system and will reduce the overall cost of the system. So the research question is that how does the storage, the CGH2 tank storage, reduce the overall cost of the system? And that cost includes both the capital cost of the system and the operating and maintenance cost of the system over the lifetime of the application. So if we take a look at the economic comparison, if we look at just cost, so we know that the cost of the grid, because there is no capital cost on it and because it has only operating costs, so that's the best option if we just look at the overall cost. But if we look at the emission, then we go from the bottom to the top. The lowest row has the lowest emission, and at the same time it has the highest cost. And all of those configurations that we see are the optimal configuration of the system to cover the hydrogen load. So the lowest emission has all components, including the storage, electrolyzer, and also the grid and PV. And the net present cost of the system, and also the operating cost and the initial capital cost, as you see, all of them are higher than the, for example, first row or second row, but it gives us the lowest emission. The hydrogen tank storage, which is 20 kilogram, is the optimal size of the storage based on the cost and based on the given consumption profile of hydrogen. So if you look at the cost of each component for the last row, which is the lowest emission one, as expected, we see that PV has the highest cost, and that cost basically associated with the capital cost of the PV, because the operating cost is very, very low. And then after that, we have the cost of the grid, and that grid is because the storage tank did not provide enough hydrogen that we need, or because it was during the night, so the grid should be used. After that, we have the cost of the electrolyzer based on its size, and the hydrogen tank. After that, hydrogen tank and electrolyzer has almost the same cost. But as I mentioned, if we can increase the efficiency of the hydrogen tank, then we can guarantee that more hydrogen will cover the load with lower cost. So for example, ideally, if we increase the efficiency of the hydrogen tank from 50% to 100%, which is doubled, that means the cost will be half of 30,000, so it will be around $15,000. And finally, the system converter, which has the lowest cost among other components. For the input energy, during the summer, because there is high level of solar radiation, so more than 50% of the electricity comes from PV. However, we need grid because during night there is no radiation. But during the winter, as we go from October, November, December, January, and February, we see that more than half of the electricity comes from the grid. But overall, if we look at the whole year, we see that almost 51% of the electricity comes from PV, and 50% or 49% comes from the grid. There was an option that we could sell electricity to the grid to cover part of the cost of the capital cost of the PV. So here you see that 13.5% of the electricity that is generated by the PV is sold back to the grid to cover that cost. Then if we look at the electrolyzer output, we see that not all of the time the electrolyzer is working at its full capacity according to this graph. But in this period, we see that most of the time the electrolyzer is working at its maximum level. This graph is based on the energy produced by the electrolyzer, and this graph is based on the kilogram per hour of hydrogen that is produced by the electrolyzer throughout the year. And as you see, this is the capacity or the maximum level of the electrolyzer output. So based on those graphs, we can say that electrolyzer is not, for example, designed oversized or undersized, because it was used at its highest capacity in some periods, but not in other periods. And at least half, it was working at half capacity and more than that. But if you look at the stored hydrogen, we see that we have the low level of stored hydrogen because it was being used during winter. But during summer, no, it was almost at its highest capacity. And it means that the electricity that comes from the PV was directly being used by the electrolyzer to cover the load. And because the residential load for hydrogen during summer is low, but during winter is high. And those orange region in this graph also shows that the stored hydrogen is almost not being used during summer. Thank you for your attention. These are the main references that I use for this presentation. And this work was supported by Esip, which is the Energy System Integration Partnership Program. Thank you and have a great day.